5,
You got it.
5, 5. Other 5.
Yeah.
Good catch.
Am I right? Is that right?
Yeah?
Oh. Ooh. So,
No, yeah.
now what? Because I see that there, but I don't see anything. I've actually dealt with everything.
Yeah?
I do want a dot there. Because I have dot, anti-dot, dot. But I have an anti-dot even more to the left. It's kind of like undoing myself. I can do it. All correct mathematics is correct.
Yeah, right there.
It's just a question that's helpful.
No.
Or, you might notice something right now. This is exactly the anti-version of what I'm looking for. It's the exact opposite. So this polynomial division has answer 4x cubed plus 2x squared plus 5x minus 1. Crazy. Alright. When I was teaching high school for 10 years, I absolutely did dots and boxes with my kids. I had no shame starting exactly where I did with you guys today. When I was a child in a vending machine, I call it through on machine, da 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 da. Go back to basics. It never hurts to go back to basics. One thing that really shocked me and alarmed me, and I never spoke out about it, is that so much of the culture of my high school colleagues was, well, these kids should know it by now, therefore don't waste time on it. No, please, please, please. It takes many years to process stuff. There's no harm in going over stuff again. Because every time you go over a second time, or third time, or fifth time, you see it in new, deeper context, in new light. This notion that we're done with a concept is absurd. And it's kind of insulting to me as human beings. I know I'm very slow at stuff. Please show me stuff 14 times, then I'm going to forget it all. Show me again in another 4 years' time. This is the nature of learning. No shame in going back to basics. But I've gone back to the basics in a way that has some real context and play with them. They had the same epiphany about 276 divided by 12 as a grade 5 problem, and 2x squared plus 6 divided by x plus 2 as a high school algebra problem. And suddenly they own it all. And they can do all this too. Now, I admit some of the stuff gets thorny. I admit that what you're doing, you're lucking out. You're not doing this on pencil and paper. Being able to actually know about dots helps a lot. This dots and boxes method is lousy as a paper and pencil technique. Absolutely lousy. You get so tired of drawing boxes, you get so tired of drawing dots, and kids will start making shortcuts for themselves. They won't actually bother drawing the dots anymore. They'll just write the numbers and see what's going on with the numbers. They won't even stop drawing the boxes after a while, just write the numbers. They might draw like lines separating the numbers or something. They start inventing a process that to me looks strange and bizarre out. It looks just as bizarre as long division does. But that's the nature of it. You start doing this because those standard algorithms are the end result of trying to get shortcuts because you've got the conceptual understanding. However, I will still say that my kids right now, dots and boxes is still a lousy, actual, practical paper and pencil method. But it's absolutely brilliant for conceptual mind understanding. They own it. Then what do I do as a teacher? Lo and behold, the area model comes back in the light, and I'll do polynomial division by the area model, which is actually much friendlier on paper. In fact, this lass here decided not to do this one on dots and boxes because it was just too messy. She drew a great big rectangle to reverse area model on it. And then this serves another powerful message for kids. Whoa, two separate areas of mathematics have just clashed together to produce the same thing. We just don't, I mean, is that one of the Alberta things to make connections or something? Yep. Whoa, let's make a major connection. Square bracket C, am I right, or something?
Yep.
There we go. Square bracket V, done. Square bracket C, done. And then, actually, for actual work, kids tend to prefer the area model because actually you can do it on paper fairly quickly, no redrawing dots and stuff. It's less tedious in a practical sense. However, that's just for the practicalities, not because of the mind understanding. So you notice I was not ever teaching for getting to speed answers quickly. If I want to get speed answers quickly with my kids, I would have done traditional long division, which you do. I was actually taught to do this beast this way. Was anyone else ever taught to do it that way? Oh my heavens. I didn't understand it in grade 5, I surely didn't understand when I was doing that sort of thing. But if I want to get speed answers quickly, I have to tell my kids to do it. That's not my goal. Not my goal. Now, what I also want to do, probably after the break, since it's coming, is get into decimals. Because I believe there is a part of 9th grade, if I remember, from what we did on the whiteboard last June, about kids need to know the difference between rational and irrational numbers. This is in the US, I am deeply perturbed by that being one of the Common Core state standards. Because nowhere in the curriculum do they actually give an example with reason of why a particular number is actually irrational. Kids just know the square root of 2 is irrational. They just know that pi is irrational. Well, they know because we told them to just know it. They've never been shown a reason why these things are actually irrational. In fact, they've never even been given an example of a single irrational number. They're just told, just know it. And then there's all these test questions about which numbers are rational or irrational. They've never been given an actual example of a rational number, only just been told, memorize that root 2 is irrational. And just kind of know that root 6 is irrational, that cube root of 8 is also irrational. No, cube root of 9 is also irrational, things like that. Just kind of know it. So another place that dots and boxes can really intersect well with the Alberta curriculum, by the way, that is grade 8 in the US. I think it's grade 9 for you. Let's talk about decimals. And I want to show you how to use this as a place to actually give kids an example of an actual irrational number and have them find more of their own. And it's another one of these mind-blowing processes that's just like, well, why didn't people just do this in the first place? I don't know. So I say we should do it in the first place. But the remaining 12 minutes, there's 7 minutes before lunch, let me show you how far we can actually go with this. Let's do a really unusual division problem. Let's do the polynomial 1 divided by 1 minus x. It is so sparse, it's hard to know what it means. Here's what the polynomial 1 looks like. Pretty sparse picture. You're looking for 1 minus x. What does 1 minus x look like? Anti-dot, dot. So this division problem is looking for this pattern in this very empty picture. Can you do it?
I know, but I have to
That's 3 pi. Yeah.
1 minus x. So you put your minus x.
So I'm gonna put my 1 over here because it's gonna work this way.
Yeah.
Oh, okay.
Start with
So
-1.
every example I've done today is valid with that standard. Yeah.
Just
Hold
constantly.
on, but hold on.
Essentially,
Why is it one anti? Why isn't it anti 1 here? Why can't I go anti here?
Yeah.
Is that what I called them on it?
Well, you're gonna work this way.
It's gonna work the way we've been doing it.
So
that is such
we already agreed
unsure of the trust me, that's.
that this is that's what we have. So the anti version of
Alright. And remember, if there's anything in life you want,
that.
just make it happen.
So do that.
So there's anything in life you want right now?
Put the 1 here.
I would love an anti-dot there. Yay, what we want.
I don't want to change that for me.
Again!
Oh, you're just doing it backwards. So it should be a brat.
Again!
No.
Going left to right. I get it.
Again! 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 And on and on and on forever. Am I do that forever? So now the question is, how do I read that answer?
X to the power of n plus x to the power of n minus 1, like your x.
How far n am I going to?
I don't know. Be infinitely.
Infinitely, so watch out. So maybe start at this end. What about just going 1 plus x plus x squared plus x cubed, infinitely far? Tell me, is this a high school formula?
I bet you it's called infinite something.
But you might have it written the other way around. Maybe it appears in the books this way.
A screen between you two.
Does that look familiar?
Separate you two.
The geometric series formula.
How would you do it if you were going to the in the other direction? Because that's how I looked at it. I saw the one.
That is true. All right. So then that means you want boxes not just going infinitely far to the left.
I just wanted to do it to the right.
You want some boxes to the right as well then, which we don't have yet.
I think he's saying he only did it to the right. That's
Yeah, I didn't do it to the left. I just did it to the right.
Right, but you had no boxes there.
So I can do whatever I want.
Correct. So what do those boxes mean for you?
Well, those would be like fractions or.
Brilliant. So you've just now discovered a want to do decimals. So I wouldn't call them decimals in the next one machine. I guess I'll call them eximals. Because deci is the prefix for 10. So the 10 machine. So definitely, that is beautiful. You've just discovered a need for what I want to do after our lunch. Let's actually put boxes to the right and talk about decimals. And we'll come back to the example and show exactly how you do this one even in the decimal world.
But you should come see what he did after.
Alright.
I think you're going to have x to the -1.
Yeah, you'll have 1x, 1x squared, 1x cubed. It'll be fun. Yeah.
He went the other way.
Yeah, so you got negative 1 of x squared, negative 1 of x cubed, negative 1 of x. Yeah, absolutely valid. All correct math is correct. Alright, however, just to check. Put x equals 1/3 into this formula. What's it telling me?
1/3. 1/9.
1 plus a third plus a ninth
Plus
plus a
27.
27 plus 3 over 8.
181. 244.
Alright. Oh, I don't like fractions within fractions myself. I hate hard work. Did I mention that as a mathematician? So let me get rid of the thirdness of this and multiply the total by 3. What do I get? 3/2. Beautiful. Can I subtract 1 from both sides? The reason I'm doing that is I think we had this formula earlier today, didn't we? And what's 1.5 take away 1? Bingo, we're back to where we were. With those garden paths. You know, you just bring it all sort of circling in on itself. It's just like crazy. That is crazy. Alright. So to set up after lunch, let me go back just for simple starters here, the 10-1 machine. And I will tell you, I agree. I find it perturbing to have something going infinitely far to the left only. Asymmetry just doesn't feel right to me as a mathematician. Why does correlation to the leftness? Why can't we just put boxes to the right as well? Well, we can, we have to see if we make sense of them. I know these dots are worth 1, these are worth 10, these are worth 100, these are worth 1,000, these are worth 10,000. How on earth can I make sense of dots going the other direction as well? Going opposite direction, yeah. But it's a 10-1 machine, so I know that 10 of these, whatever they are, has to be the same as one of those. It's almost a dot here, worth. Yes, 10 1/10 makes 1. 10 1/100 makes 1/10. So on. So we've now discovered decimals. And most people put a little point here to separate the left boxes and the right boxes and call it a decimal point in a 10-1 machine. Because how many years in a decade? 10. Deci means 10. What's the 10th month of the year?
October.
What's the 12th? What's December then? Actually, Oct means 8, doesn't it? And October's not the 8th month of the year. Nova means 9. November's not the 9th month of the year. Deci means 10. December's not the 10th month of the year. Sept means 7. September's not the 7th month of the year. What's going on with that?
Old calendar.
Old calendar. It
Based
used
on
to be that March was the first month of the year. And then some people did some Gregorian people did some like adjustments and stuff. But before then, there's also a couple of Roman emperors that started these months named after themselves as well. Who were they? Julius in July,
August.
Augustus for August. So suddenly it became 12 months in a year. And I went back and forth between March being the first month and January being the first month and March being the first month and January being the first over the centuries, until finally in like the Gregorian calendar settled it down. We're going to make January the first month, and I know our naming system's off, but those September, October, November, December, which used to be the 7th, 8th, 9th, and 10th months of the year, oh, this got bumped by 2. And now the 9th, 10th, and 11th, 12th months of the year. Messy history of the calendar gets those prefixes out of whack. Stories, left, right, and center. All right, now it's lunchtime. We'll do decimals when we get back.
So we are walking across the street to the Red Rock Barbecue.
Yes, we
they are
are.
waiting for 20 teachers to be there in 2 minutes.
20 cool teachers.
Well, I definitely said that.
Fabulous teachers.